Good afternoon, everyone. I'm Will from IES Red Team of ByteDance. It's an honor for us to be here. Thanks to Black Hack for invitation, and thank you all for attending. Today, I'm excited to share with you our research, mini app but great impact, new ways to compromise on mobile apps. Generally, attacks on mobile apps, usually from native apps, web pages, and networks. Our research introduced new ways to exploit mobile apps through mini apps. We hope our presentation will incite and inspire you with some new and productive idea and help improve the security of mobile apps. Okay, let me talk about ourselves for a little bit. My name is Wen Wei, and my colleague next to me is Cao Xiangyu. There are other contributors who are not here today, and our team members are security research and developers at IES Red Team. Our team members focus on privacy and data protection research, and our contributors are also bug hunters interested in mobile, web, and cloud security. Our team has spoken at Black Hat USA, Europe, and Asia. Here is the outline of our presentation. First, I will introduce the background of our research. What is a mini app? The difference between mini apps, native apps, and web apps. I think many people have questions about this, just like I did before. I will also introduce the basic structure of mini apps in this chapter, including its document API and security mechanism. In the second chapter, I will talk about how we conduct security assessment on mini apps, focus on its API, covering its network and file capabilities, compare with native app and web apps on browser. In the third chapter, I will discuss the further analysis of the security risks that may exist in its architecture, such as how to discover and use hidden APIs, and how to apply prototype chain attack on mini apps. After discussing the security issues of mini apps, we will introduce how to fix and mitigate these risks. And finally, we summarize our overall sharing, including our research ideas, research results, and the direction we think can be further explored in the future. Let me introduce the background of mini app first. Mini app represent a cross-platform solution, relies on web technologies and the capabilities provided by native apps. With just one code, mini app can be launched and run on Android, iOS, and even PC platform. A super app is a native app that functions as a platform for mini apps, which supplies the necessary resources for mini apps. In this architecture, the super app is responsible for providing platform resources and distributing the different mini apps. Users can launch a mini app simply by just clicking a link or scan a QR code. On the right side is the architecture diagram of mini apps. The capabilities of mini apps don't rely on the operating systems, but rather on the platform super apps offers. The engines of mini apps use V8 or JavaScript core. Developers can invoke native capabilities in the logic layer through JavaScript code. These capabilities include file operations functions, network access functions, media resource functions, and its ability to get the location managing and so on. Here is the difference between mini app, web app, and native app. Mini apps are deployed as packages, while web apps relies on web resources and server, and native Android app use APK. They also have different engines and dependencies. From our study, we can summarize the following advantage of a mini app. Compared to web apps, mini apps operate on platform provided by a super app, offering stronger capabilities for interaction with native functionalities of operating systems. Compared to native apps, mini apps relies on web technologies, making them lighter and easy to use. They don't need to download and install the APK files, and they are easy to update. Here we list some basic capabilities of mini apps. In short, mini app developers can use a series of APIs to interact with super apps, such as use this API to manage the file systems or access network, get location info, and access media, open camera, microphone, or access the user album. While mini apps possess powerful capabilities similar to native app, we need to pay more attention to its security issues. For example, we need to check whether the super app has restricted the permissions of these APIs and limited mini app to access resources. This involves both vertical and horizontal permission check. In detail, vertical permission check means only mini apps authorized by user can use sensitive API, and horizontal permission means a mini app should only be able to read its own data. It cannot read the resource of other mini apps or the resource of the super app. Moreover, refer to the implementation of mobile apps. Mini apps should have a sandbox mechanisms. This may include aspects like data storage sandboxes, code execution permissions, and isolation of the runtime environment. After having a general understanding of mini apps, let's turn to the risk of mini apps. For the risk assessment of mini apps, we still start from the compare study. By studying the security mechanism of web app and native app, we focus on the following aspects: access control, sandbox storage, same origin policies, and process isolations. In this chapter, we will discuss file and network related topics. The others will be discussed in a later chapter. Let's start by analyzing the function related to the file systems. After studying 9 applications, we identified the following common APIs: read file, write file, and unzip. We do the security test for these APIs, try to access or override the files outside the mini app storage space. For example, reading the super app's cookie file or override the executable files such as DEX, APK, or SO file, which may cause remote code executions. According to our assessment result, we found 2 apps have path traversal risk and permission and parameter input. 3 apps are affected by symbolic link attack, and combined unzip and symbolic link attack, 5 apps are vulnerable. This diagram shows the complete attack process. A host super app can run multiple apps in this picture with their file systems isolated by permissions. Attack purpose is access the file outside the sandbox. Here is the detailed attack flow. The attacker creates a bad mini app and generate a quick launch QR code or a bad short link. When a user scans this QR code, the bad mini app is launched within the super app, just similar to the one-click attack. Then, this bad mini app invokes the special graphic API to launch a path traversal attack. This means attackers can escape to the host's file space, potentially leading to credential leaks, even code executions. Next, we conduct security testing on network capabilities. Our target are APIs making outbound requests, such as request API and upload API. Through our research, we found many applications directly reuse the host's basic network capabilities, which may lead to server risks. The most immediate issue is using the request API to send a request to third-party website within user information. During our study, we identified one super app that sent user credentials to a third-party website. Besides, we found 8 apps request with credentials to first-party website. In this case, a mini app deployed by a third party can send requests to the host website with user cookie. These features violate the design principle of the same origin policies. Additionally, due to the feature of the request APIs, the mini app can fully access response data through JavaScript callbacks. This leads to not only CSRF risk, but also information leakage. This diagram shows the completed attack process. As we can see, a malicious mini app is developed by the attacker. It can send a request to the super app server website, like the path name, for example, get user info. Then, because this API sends requests with user cookies, the server responds the user data to this function call. Then, this malicious mini app is able to get user data. Here is the basic security assessment of mini app architecture. We mainly conduct assessment based on the capabilities provided by the developer document and combine it with general knowledge of web security and mobile security. Through in-depth research on the security architecture of the mini app, we found many potential security risks never mentioned in developer documents. These vulnerabilities are caused by the features of mini apps architecture. Next, my colleague Xiangyu will introduce them in detail.
Thank Will for setting the stage perfectly. Now it's my turn, and my name is Cao Xiangyu. Well, Will have provided us with a clear introduction to mini apps and their risk assessments. I will take you deeper into the specifics and explore how mini apps can be leveraged to execute some remarkable exploits. First, I'd like to introduce the concept of hidden APIs. Taking the iOS system as an example, Apple officially provides developer documentation outlining the APIs available for developers to use. However, many developers still try to use private APIs that are not in the documentation to implement special functionalities or even to bypass system security restrictions. Similarly, developers of mini apps can leverage hidden APIs to access capabilities beyond the intended restrictions, potentially compromising user security. And this raises two important questions about mini apps' hidden APIs. How can we discover hidden APIs and how can we effectively invoke them? Let's look at how to discover hidden APIs within mini apps. First method is JS core analysis. As mentioned earlier, JS core acts as a bridge between mini apps and the super app. All API calls to native components are uniformly managed by JS core. It's worth noting that you can easily obtain detailed JS core source code by using mini app developer tools or by connecting and debugging directly on a mobile device. Therefore, analyzing JS core is a highly effective method for discovering hidden APIs. The second method is app reversal, which involves reversing the super app's code responsible for handling mini app's API logic. Because regardless of how mini app APIs are invoked, finally, this course will interact with the native layer. Although starting analysis from the native layer can be more complex, it remains the most comprehensive and reliable method for uncovering all hidden APIs. And by examining both the mini app itself and the super app, we have identified two very effective and reliable methods to systematically discover hidden APIs. Through our practice, these methods have indeed uncovered many high-risk APIs capable of exploits such as stealing users' login credentials and accessing private data. And after the introduction of how to discover hidden APIs, I will introduce you the methods to evoke them. But before we proceed, I need to explain how developers implement mini apps functionalities. To to facilitate unified management and enhance developers' efficiency. Mini-apps encapsulate the APIs that developers need to call within a global variable. For instance, under a global variable named X, all the API capabilities are included, such as x.request, x.getLocation, and so on. Subsequently, developers must tailor their specific requirements by following the description in the official developer documentation. Use x.request to execute network requests that comply with the mini-app standards. This design introduces two potential methods for invoking hidden APIs. And first is direct invocation. The simplest approach is invoking hidden APIs directly through the public global variables such as X. We can examine all functions of this global variable X to identify any hidden APIs not documented officially and invoke them directly. For instance, we identified a method named hidden request under the public global variables X. Any request initiated by this method inherently includes the user's login credentials, posing a significant risk of account theft. And the second is privileged variables. Invoking hidden APIs through privileged global variables offers another pathway, as what is shown here. After a developer invokes a public API, the call traverses through JS core and eventually reaches the super app via a JSP method named applyNative. With the API name provided as a parameter, direct access to the applyNative method would enable unrestricted invocation of hidden APIs. During our testing, we have confirmed numerous cases where hidden APIs can be invoked through privileged global variables. For example, by enumerating all global variables, we successfully located a variable equipped with applyNative capability and finally invoked hidden APIs directly through the global this.testwall.conative. After discovering these problems of hidden APIs, we immediately reported the risks to the corresponding companies and received prompt responses and fixes. Although the updated mini-app system did not remove the hidden APIs entirely for some reason, it increased the invocation restrictions on them. However, in our subsequent research, we identified a bypass method called prototype chain pollution. The core principle behind the prototype chain pollution is to hijack key functions by replacing their original logic. For example, as shown in the image, we hijacked the includes method on array.prototype and inserted our custom logic. Originally, calling whitelist.includes AAA should return true. However, after applying prototype chain pollution, we successfully modified the behavior so that the method returns false. Similarly, by exploiting such pollution, we could bypass restrictions and still successfully invoke hidden APIs. Let's look at a specific case. Initially, the mini-app system allowed direct API calls, but later introduced a private API blacklist restriction. Whenever a mini-app tries to invoke an API listed on this blacklist, JS core intercepts and blocks the call to native. However, through prototype chain pollution, we successfully hijacked the includes method, modifying its original logic. This allowed specific hidden APIs to bypass blacklist detection. Consequently, when the mini-app system checks if an API is in blacklist using the includes method, our modified logic completely bypasses the intended verifications. As a result, we can freely evoke hidden APIs despite all restrictions. Actually, by the way, in reality, there are many other ways to exploit prototype chain pollution. We hope the example shows potential attack surfaces clearly and encourage further exploration. Now, after understanding various attack methods, let's focus on how super apps can mitigate or fix these issues. For each identified attack method, we have provided mitigation suggestions such as domain name verification and using object freeze. Generally, these suggestions can be summarized into three core mitigation principles. First, sandbox isolation. Super apps should create independent operating environments for each mini app to ensure isolation and prevent mutual interference. Second is permission control. Super apps should restrictly manage mini app access rights, including permissions to the file system, network, storage, and device resources. The third is runtime security. Super apps should monitor and control the OS runtime environment of mini apps, managing resources like memory, CPU, and GPU usage to prevent malicious code from causing excessive resource consumption or damage. And before concluding, let's briefly recap our presentation. We started by comparing mini apps, web applications, and native applications. Then we conducted a detailed risk assessment focusing on file system and network APIs, highlighting an in-depth risk analysis of hidden APIs and global variables. Additionally, we introduced the concept of prototype chain pollution, a common web security issue, into the mobile security context. Finally, we provided comprehensive security recommendations to mitigate these risks. We are honored to have the opportunity to share our research with you today. Thank you very much for your attention.